Welcome to Pratidhwani, where we try to humanize science. I'm your host, G.V. Pavan Kumar. It is my pleasure to introduce the guest on this episode, Arindam Ghosh. Arindam is a professor at the Department of Physics, Indian Institute of Science in Bangalore. Arindam did his PhD from Indian Institute of Science. In fact, he was one of the first and the earliest integrated PhD students to graduate from IISc. Arindam is very well known for his work on experimental condensed matter physics, and his research interest includes various aspects of condensed matter systems, including two-dimensional materials. And in recent times, he has also developed very interesting quantum technologies using condensed matter systems. Arindam also is a technology developer, and he holds not only a few patents, but also is actively involved in developing specific kind of policies for cutting edge technology, which includes quantum systems per se. In this particular episode, we discussed about his biography, specifically how he became an experimentalist, his exposure at St. Xavier's College in Kolkata, and how it really motivated him to do good work, and his experience as an integrated PhD student at IISc, and specifically the influence of teachers throughout his career. And another aspect which we discussed about is his attraction towards the unconventional approaches, which has motivated him to do very good work. The highlight of the specific discussion was also on his interest in cricket. In fact, he is a very accomplished cricketer, so much so that he has even played with Saurav Ganguly, Rahul Dravid, Grant Flower, and such stalwarts. And he talks about his interest in cricket and how it helps him to become a better researcher. He also mentions about the interaction which he has with his brother Ambarish, and how it has had a positive implication. There's also a very nice story about him preparing Josephson junctions when he was a research student, a starting research student, and his interaction with Professor Arup Rai Chaudhary, who really gave him the very nice directions to become an excellent researcher. It also kind of specifically motivates students to understand what it takes for one to become an experimental physicist. And Arindam mentions his experience of noise measurement, and how he encourages his students to develop new technology, and his own experience in using statistical measurement in condensed matter systems, which has played a very important role in developing not only interesting physics, but also developing some interesting technologies based on that. We also discussed about his experience in working at Cavendish Laboratory in Cambridge University, which really helped him to kind of redirect some of his approaches of doing research, including device physics, and his return to India in mid 2000s, and what it took him, what motivated him to come back, and what kind of approaches he took to do his research. For example, he talks about the bottom-up approaches. He specifically also describes his very interesting work on graphene, which really led to some very interesting and important viewpoints on how to use van der Waals heterostructures for some kind of an optical measurements. He also mentions about the importance of building instruments and the instrumentation development in PhD work. We also discussed about how to really utilize the vast and excellent human resource which is available in India, and he also tells us about his own interest in and his viewpoints in how technological benefits can be catered towards the societal benefits, and how there can be a very nice coherence between these aspects of it. There's also a very nice segment in Bengali where he describes about his research, and he also tells us about his interest for gymming, for example, and how he motivates his students to do the same. And finally, he describes his future plans of looking at quantum technologies, and also his interest in policy matters, and how that actually can further foster specific kind of developments in the Indian academia per se. Overall, it was an excellent discussion, and as usual, you learn a lot whenever you talk with Arindam. He has motivated a lot of researchers, and I'm sure he'll continue to do the same. And this conversation is just a reflection of the same aspect of Arindam. So this is Pratidwani, where we try to humanize experimental condensed matter physics with Arindam Ghosh. Arindam, welcome to Pratidwani, where we try to humanize science. I'm delighted that you could join today on a Sunday morning. Welcome to Pratidwani.
Thank you, Pawan. Delighted to be here with you.
So, Arindam, please tell us about your biographical trajectory and importantly, how did you become an outstanding experimentalist, scientist, and also somebody who is now leading some very interesting efforts in Indian science?
Right. Let me correct you at the outset, Pawan. You added an adjective, outstanding experimentalist. So I would like to tell you how I became an experimentalist. I think that's more important to answer.
Absolutely.
So I was born and brought up in Kolkata, and I was raised in a very theoretical and very academic atmosphere where we always felt that physics is large. Okay, so I went to Balagazi Government High School, and then I went to St. Xavier's College for my higher secondary and the Bachelor's of Science. I'm talking about 1980s, and at that time, Kolkata was a crux, and it had the culture of doing science, and science was taken extremely with respect, and I think that still continues. It's not changed too much.
You're right.
But the best students, if you are a good student, then you were naturally drawn to science and ask very deep questions. The question was whether it was experiment that was a strong culture, and at that point of time, it was not. Theoretical physics was always a strong attractor of good students. So you needed very high quality people to guide you to do experiments. So after I finished my higher secondary at St. Xavier's College and then started my BSc, I was naturally drawn to physics. That was a good start. And St. Xavier's College at that time had some set of fantastic teachers. I still remember the days when I was told at the college, when I did not go for standard engineering programs in IIT, I chose to deny admission there. I was told at the college that, why are you going to science, to go to physics? But I said, look at the teachers that we have. And look at when they taught us in higher secondary, science was naturally becoming a preferred subject. But really, the experimental science, I have to say, got, I would say, I became inspired to do experimental science when I met one of my best teachers during my lifetime, I would say, Professor Manindranath Mitra. He was head of the department of Bidhannagar College. I have seen a lot of people, but in Calcutta at that time, you would find dedicated teachers who just had fun in telling students how they felt about the science, about the concepts, about what they understand. And I remember I did some experiments during my BSc days, and I have to say with great shame that I did tinker a few data points here and there because I had to couple to the existing theories that my experiments are in tune with them. Then I met Professor Mitra in his residence one day, and he said, "Okay, why don't you get your lab notebook?" So I got my lab notebook to him, and I'm talking about 1989. And he browsed through that notebook, and he said that, okay, so you got this result. I said, okay, I kept quiet and I said, yes, maybe. And then he said, okay, why don't you calculate the error your experiment will have for you to have this number repeated experiment in repeated experimental trials.
Nice.
And then he proved that the kind of equipment I was using, which was a thermometer, which was a scale, ruler, I still remember it was a Jaeger's method of measuring surface tension of water. And he proved to me in front of me that experiment cannot give the right result if I am to use the equipment that I'm using in the laboratory. Neither my teachers in college or I myself looked at it, experiment in that way. Wonderful. I will say, Pawan, that day I became an experimentalist.
Fantastic.
The joy of doing experiments, finding out where the details that you need to take a note of was an absolute pleasure.
Nice.
So then I became, of course, I went to IISc for my master's and my PhD, and I never had the doubt that I would become an experimentalist in my future. My question was which field, but I eventually chose condensed matter physics and continued experiments in that.
Yeah, we're going to come to that particular aspect of your transition into condensed matter. Before that, your formative years, how was it growing up in terms of your environment at home? What kind of environment were you growing up, and what kind of influences you had at your residence, especially your parents and siblings? If you can just let us know a little bit more.
Right. So the home atmosphere is the crucial atmosphere for any development, and I had probably the most, I would say, conducive atmosphere at home, which would let me take my natural instinct and move towards that direction. My mother herself was a highly educated woman, and she's a master's in physiology at her age, at her time. So she was well in the education zone, and she had a higher education. My father, on the other hand, was one of the most calming and encouraging person I have met ever, actually, and one of the most forward-thinking person. He used to say that you must do whatever you feel excited by.
Wonderful.
And this was true for both me and my brother. We are two siblings, and we were allowed to pursue our interest from the word go. And I think that's so much important. You see, I'm coming from an era where, and probably that era continues today, where people are asked to take professional courses like engineering by parents as much as anybody else, peers, right?
Yes.
I had parents, particularly my father, I would say, who put his foot down and say, you must do what you want to do. And it made it so much easier for me to do science at home that it's unbelievable that at that time a person would be able to go beyond environment and advise their kids to take up topic of their interest. So I enjoyed that initial start, I have to say. But there are certain intrinsic tendencies in me. I always wanted to do things which are unnatural. Or my mother always says that whenever I used to take my tricycle, I would go in a gadda rather than go in straight on a plain road. So I always wanted to do things differently, and I always got attracted to something uncommon. Even during my college days, I remember Professor Bhanjo was one of the most respected teachers. And he gave a question in our first year BSc of one question of 80 marks and other questions of small questions of 10 marks or 8 marks each of 10 questions. I was the only one who attempted the 80 marks question and got it wrong. Okay, so I tried my best and I got it wrong, and I could not answer any question. I was about to fail.
Wonderful.
So and Professor Bhanjo, when he checked all the answer sheets and then distributing the answer sheets with his comments, he said, "Okay, come here." And And he said that the reason you got wrong is because I made a mistake in one of the numbers of the question.
Wow.
So
Okay.
I give you full marks. So he gave me full marks. Okay. So
Nice.
as I said in the beginning, that it's a home atmosphere, and my intrinsic attraction towards unconventional actually made
Nice.
me move the career path that I've taken.
Wonderful. Wonderful. So, it is a very important aspect that this kind of formative years also play important role not only in developing interest in a particular subject like physics in your case, but you would have also been influenced with a lot of things which is happening around. Because I'll come to a point which I want to emphasize going further, that Arindam is also a very good cricketer. He actually has played very competitive kind of
Yes,
level
I
of
did.
sport. So this is something very important, Arindam, because there is a notion, especially among general public, that scientists are holed up in their laboratory and
Right,
and do not have varied interest in other things. Uh,
right,
Given that you actually did play very very well, and because I was witness to that particular thing at some point of time too.
right.
Could you please also tell us how do you develop a kind of slightly more broader interest in other things?
So, yes, I used to play cricket quite seriously since my days in Calcutta and continued in Bangalore. And even when I went to England for my postdoc, I continued playing there. I returned to India as a professor, I continued playing here as well. So in Calcutta, of course, I'm a contemporary of Saurav Ganguly, and we were in the same college way back in early 90s, 1989, 1990. And we also used to go to the same coaching club called Dukhiram in Arians College ground. Of course, he used to spank me all over the park, and it's quite embarrassing. But then when I moved to Bangalore, actually early 90s, ended up playing with Rahul Dravid also while he was in St. Joseph College here. And of course, after that, they went to England in 1994, and then the rest is history, I would say. But then, what happened is after I completed in Bangalore my PhD, I went to Cambridge for a postdoc, and I ended up playing more interesting and more competitive cricket, because while doing PhD, really you do not have much time for competitive cricket. But in postdoc, I naturally got included in a team which is to have people who are professional in many ways. And there I came in touch with some of the key members of some of these national teams. For example, I think Grant Flower and Zimbabwe, then Matthew Sinclair, New Zealand, then Stuart Williams, who played for West Indies for a while. And I saw them at a close quarter, and I found that there is a deep commonality between professions of all type. Whether it's a profession in cricket or it's a profession in physics or science. And if you go through a dry period, whether it's in terms of runs on the cricket field or in terms of a number of papers in professional science, I think the stress is very similar. You feel that you are losing it, or you are getting worried about your existence, about professional existence, I mean, and you try to continuously build on the failures. I mean, so that's how different professions come together. It was a great learning experience for me, and which also made me continue cricket even after I became a faculty at the Indian Institute of Science way back in mid 2000s. I continued playing cricket. That's because it not just gave me the opportunity to reset, the stress of the lab, unproductive periods, etc. But it also allowed me to utilize my learning to reduce the work stress, for example, and also make great friends. There is no doubt about it. And I would emphasize that I never felt playing cricket, although I spent lots of Sunday or weekend afternoons playing cricket. I never felt that it's a wastage of time. Because you would think that you are staying away from the lab or even socializing with friends or whatever it is. I always felt that's a great time, because that allowed me to work better after the phase. And I used to be tired, but I used to be satisfied, and I used to feel that, okay, it's an evening or afternoon well spent, or a day well spent. So I always felt that sports had been an integral component of my journey, and cricket probably was the key component in that.
Absolutely, this is something extremely important, and you also very nicely, uh, kind of connected the domains of sports to the research, which is probably one of the very important connections one can make. In fact, that gives furthermore the reason why one should have such kind of deviations while doing research and other things. Okay, Arindam, could you please tell us about your siblings a little bit more?
Yes, Pavan, I think this is one of the points I must emphasize, because otherwise I will not get dinner at home. So, when we were growing up, it's just me and my brother. And one of the luckiest point I would say in my professional growth, personal and professional growth, is to have a sibling who appreciates and understands your work.
Wonderful,
Of course,
wonderful.
he understands my uh, emotional and professional states in a manner that no one else can, right? Because he
Wonderful.
has observed me, and Ambarish is one of the, not just a brilliant scientist himself, but
Absolutely,
he is one
absolutely.
of the most, you know, balanced person, and he is in many ways a stabilizing factor that I have been fortunate to have around me. So
Fantastic,
this,
fantastic.
he joined IIC as a faculty since 2000, in 2010,
Mm.
and that's the part when he became, he saw and he developed his own career. But we discuss science all the time, and whenever we met, and he's one of the most versatile person to talk to, because
Absolutely.
of the ideas, because of the newness, the freshness of the ideas, and it always refreshes you talking to him whenever we are having dinner, or we're sitting with a glass of wine or whatever it is. It's a
Wonderful,
fantastic time to a
wonderful.
relaxing point, that
Yeah, yeah.
relaxes. Yeah,
Yeah, I should mention to the listeners that Ambarish Ghosh is also a physicist, a faculty member in Indian Institute of Science. And it's amazing that Arindam and Ambarish, the Ghosh brothers, have done some very, very interesting work coming out of India. And of course, I'll be linking all the web links on the show notes. But it's quite wonderful that to see the two very good scientists coming from the same family, which also reflects on the fact that the upbringing has had an important role in this, right?
that's right. Absolutely. I told you that we were just given free space to
Mm-hmm.
look after and to go for what we felt excited by, and you can see the effect of that.
Wonderful, wonderful. So now, Arindam, we will just move ahead and try to actually get a look into your developing interest in physics. So you're finishing up your school and college in Kolkata, and now, how did your transition from the college to IASC happen? Would you want to elaborate a little bit more on that?
Yeah, actually, that's very interesting, because I
Mm-hmm.
think at times there are opportunities that come, and which is quite out of the blue, and you take that, and that changes your life forever. So
Mm-hmm.
when I was trying to finish my BSc, I was still unclear about what I was going to do.
Mm-hmm.
And one day, as in 1990 or 1991, um,
Mm-hmm.
uh, one of the professors, Professor Dipankar Banerjee, I think, who went to Calcutta and
Okay.
gave a short talk and said that IIC is starting this new program, first time in India, in physics called integrated PhD program.
PhD. Yes.
Right. And if you are interested in pursuing a PhD directly after a BSc, then apply for it. Now,
Nice.
again, most of my people at my classmates, etc., were thinking the same thing. Usually, trying to take this route of masters and then trying to think what to do. So I always wanted to do something different. I said, this is it. This is what I would like to do. And then there was an exam, and I came to integrated PhD program. There were 6 of us in 1991, 92. Who were admitted in ISC's integrated PhD program. And that program, by the way, Pawan, I think you know very well, is one of the most successful programs and now adopted in almost all institutions, high tier 1 institutions in the country.
Absolutely correct.
It's one of the most successful programs of training young students into professionals and making them a doctorate or PhD degrees. And the reason it is so successful is because you train them well, train them early, and give them the opportunity to explore the interesting cutting-edge science that's going on. So I think that's the reason why this program has been so successful. But anyway, so that's when I came to ISC, did my 2-year master's course, and at the end of the master's course, we all failed miserably. Okay. Our exam, master equivalent exams, we were disasters.
Okay.
So that's when we were told, just because IISc doesn't mean that you can take things for granted. You go back and you have to give your exams. All the teachers were quite upset, and then we had to rework our master's level exam, and then eventually we all did what we had to. And then I was interested in astrophysics at that time and wanted to do observational astronomy.
Like all of us.
Like all of us, isn't it? Yes, we were all products of Stephen Hawking's Brief History of Time.
Yes, you're absolutely right. You're absolutely right.
So that was an important book at that time, and we wanted to all go for observation. I wanted to do experiments, as I told you at the beginning. So the way I could go closest to that book is to do an observational astronomy. But then I did a project in ISC as a last semester project requirement, where I made a Josephson junction with superconductors with the facilities that was there. My supervisor, Professor Arup Rachudi, told me all you had to do is to do this 30 years earlier, you would have got a Nobel Prize. But that didn't happen. But it was quite a satisfaction, I would say, that with a very minimal infrastructure, I could make this Josephson junction, modeled it, calculations, etc. Then I felt that no, condensed matter physics is an interesting topic, and I should look at it more closely. And that's when I became a PhD in this.
Wonderful. See, this opening up of interest is a very important element in an evolution of a student, because this is a kind of a perennial problem for students who generally come out of their colleges and want to get started with their research. Many a times they may actually make choices which are probably not well thought out, or I should give them the benefit, probably they are not exposed to the variety of stuff what has been done. So how does one develop this particular viewpoint? Because this is a crucial thing, because that will literally take your career into a particular path.
Yes.
And what elements do you think are important when student is thinking about such choices?
Pawan, I always tell this students, I mean, this is a point that am asked so many times. I tell them, must start by doing things, doing a topic that is the most exciting to you. If you are not doing something which is exciting, then you are wasting your time. Now, of course, what you said is absolutely right, that today I would like to do what excites me, but do I have the infrastructure? Do I have the people whom I can talk to, who can tell me what are the possibilities, and I then choose what's most exciting to me. I don't think that opportunity is always available, particularly in general. So I think with whatever resources we have around us, whether it's through internship, whether it's through existing infrastructure, existing people and laboratories, etc., we must try to continuously ask ourselves, am I getting interested and excited by what I'm doing? But that's going to take you in your right path. You start doing one, then you go to the next one, and then you go to the even next. It will eventually guide you to the right direction. You must follow your instinct and your excitement.
Nice. That's an important part of any student's journey. I should mention that even for people who would want to actually branch out of science, because there are now many avenues for students to really branch into uh, things which are related to science, need not be directly associated with the day-to-day laboratory research or theoretical research. And
Right.
the points what you just mentioned is very critical. So
So
now that you, yeah,
sorry,
yeah.
I have just a very short point. You are absolutely correct. But say, for example, today, a science background, you can always go to other kind of professions. So
Mhm.
it's not that you will have to be stuck at one particular topic or one particular direction all throughout your life. If you are doing something which is interesting, you're always keeping on learning a broad range of topics associated with that. And then
Absolutely.
you take a career path in any direction that you feel excited by in the future, right? So you are
Absolutely.
already prepared both professionally and mentally to take on any challenge that you want.
Absolutely. Uh, this might be also a bit biased because both of us have a training in physics, but the anchoring what you get to venture things into the future
Right.
from a background in physics is 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 probably one of the most versatile, right? Because that
Oh
is
yeah,
one thing.
absolutely. I think I do see every topic has its positives and negatives.
Mhm.
And see, I always give this example. Physicists always end up asking question why. So that trains you in asking the with that type of mental ability and processes. Chemists, for example, on the other side, and biologists, for example, they always deal with very complex systems.
Absolutely.
uh, so that's difficult and that's challenging and rewarding at the same time. But physicists training has a certain area where, which is why it probably appeals more to young mind. I mean,
Young mind.
we can see
Absolutely.
the number of students who want to do physics in undergraduate. Right, 50% of the ISC undergraduates want to do physics. Right,
Absolutely. It's
so
disproportionately large number,
I know
actually. Yeah.
exactly. Yeah.
Yeah. Yeah. Wonderful. So we're going to come to the stage where you are now the getting into a stream of thought where condensed matter is really occupying your mind because of the fact that you now are getting exposed to cutting edge experimental facilities and a transition from undergraduate to a research environment, especially in experiments, sometimes can be very drastic. So, how was your preparation during this transition? Were you already kind of trained in certain aspects of experiments, as you already mentioned in your college days? You did have good teachers and other people, but was this transition to really, asking questions which might not be otherwise not possible in a normal college environment? How did it prepare you to really get into that stream? And what was your formative background in that?
um During the colleges, of course, I just learned how to do experiments, and
Okay.
it's
Okay.
the fact of doing experiment was the inspiring aspect. For example, what I was told, an experimentalist always tells the world about something new because
Mhm. Mhm.
you are acting, each data point is an addition of new knowledge. I mean, theory is important too, but theories always add something that they believe that's new. Correct? So there's
Absolutely.
a there's a
Absolutely.
little difference in approach. Really. Now, experiments always uh, attracted me because I have always been detail oriented, and
Mhm.
if
Mhm.
you're an experimentalist, then you need to know the details. You need to know which wires to be soldered in what accuracy in order to get the best quality data without artifact. Right? You know this very
Absolutely.
well, Pavan. You are a
Yes.
brilliant experimentalist yourself. So experimentalists need to be needed to be detail oriented. So that was the reason why I entered experiments in the first place. The formative years, as such, was more like asking questions. I always wanted to make a new technology. My supervisor also probably saw that and then told me, okay, if you are in a laboratory, actually this is something which was the lab culture when I joined
Mhm.
ISC.
Mhm.
Anup Rai Chaudhary was my PhD supervisor, who was a PhD at Cornell, and Cornell had this very nice culture that any new PhD student will have to contribute a technology to the experimental lab.
Wonderful, wonderful.
Right? And this is a culture which I think is one of the decaying culture today. Because now experiments are becoming hard and many of the experiments can be done on existing equipments, the instrumentation and building your experiment is not something that the student or the PIs can afford to spend a time to. Often that's a problem. I'm sure you know it as much as anybody else, right?
Yes, yes.
So when I was growing up, this was the culture that was told to me. Arup told me that, look, you have to give a technology to the lab.
Nice.
And I did that, and I liked that. I created the noise measurement setup at that point of time.
Yes.
And
yes.
in 1994, 95, when I was building it up, and I can tell about 30 students probably at least graduated from the program that I wrote in noise measurements.
Absolutely, absolutely.
You know, nearly 30 years ago, 20, 25, 26, 27 years ago. So I always tell this to students as well, that everybody needs to develop one technology. Because it is, when you try to develop in one technology, you will naturally have to think there will be problems, and how you solve that problem will tell you how systematic mind you have to address a problem.
Wonderful, wonderful.
And that has been my approach, and I continue that today. I mean, I think as an experimentalist, you know, you are an experimentalist, that when you are able to solve a problem systematically, in a systematic manner.
Absolutely. There are 2 points which you mentioned, which I've noted down. One is attention to detail and being systematic. You know, these are kind of bloodlines of being an experimentalist,
Yes,
because
absolutely.
you would really have to think quite a lot about these aspects when one is becoming an experimentalist. I'm not telling that theoreticians need not be, but in experiments you'll have to probably also be kind of sensitive to the local environment in which you are doing an experiment and things like
Of
that.
course.
That's important. So one of the aspects during your work, especially in your formative years, when I was doing some background kind of research for the conversation, is that you, first of all, as you mentioned, this noise aspect, especially the 1/f noise, became a rage. You know, it was something what you and Professor Rai Chaudhary really developed this, and it turned out to be a very important contribution towards looking at condensed matter systems. Could you please elaborate a little bit about that phase of your PhD when you were trying to develop it? And as you mentioned, it really played a critical role in influencing a lot more of research coming out of that viewpoint. Could you please tell
Right.
us a little bit?
Certainly. So, yeah, you are absolutely right, Pawan. At that point of time, I was probably the first student in India who started measuring noise as a signal.
Absolutely, absolutely.
Right. So the goal was to extract noise and find out what information about a system that it provides. And I have to say a word about Professor Arup Rai Chaudhary's vision here.
Okay.
You know, as a function, as a PI, you need to have that confidence to ask your student to do something, and you need to have that depth of your own understanding. So I have to acknowledge his original support, because that's not a field that I chose spontaneously. It was
Okay.
through Arup's instruction that, Arindam, you may want to take a look at this field. Then I started developing the technology. And
Wonderful.
what was good is that in about 2 years, I developed a system by looking at both analog and digital. At that point of time, you know, digital equipments were coming into play. Digital signal processing was coming into play in a big way. So I took advantage of those emerging techniques that was becoming available to experimentalists, and used them to extract noise in the most accurate manner. In about 2 years in IISc, we developed a noise measurement setup which could measure picovolt level of noise background. And
Wonderful.
using that, we could measure the Boltzmann constant, because the noise
Yes.
background is the Johnson noise, 4 kBTR.
Johnson.
And I was one of my most exciting day in my PhD career was the first time when I measured a background which essentially was exactly equal to 4 kBTR. And from there, I could get the Boltzmann constant of 10 to the power of minus 23.
Wonderful.
So that was a real satisfaction and achievement from my personal achievement, you can say. But then what happened is that I started looking at physics of the systems, different systems, with this new technique. And I realized that noise will give you information that is standard current voltage characteristics, which most of us always do, is simply not available. You get a completely new type of information. Not only information about how to reduce the noise so that you can get better systems, but also how you can use noise to look at new phases, new quantum phases, new structural phases, for example.
Absolutely.
Okay. And at that point of time, I was trying to measure noise in everything.
Wonderful.
I went to a student, one of my roommate's laboratory. I do not know whether you know about this, and found a nickel titanium wire.
Yes.
So there's a long story of that. But anyway, so I think I was measuring noise and everything, and I was having great fun measuring.
Wonderful. I have to also mention, because while I was going through some of your formative work, you are also probably one of the first to look into the perovskite systems from a noise viewpoint. And of course, perovskite was kind of very well known in Indian community, especially in the Bangalore condensed matter community, even before perovskites became very important materials going further. Would you want to also just mention what was the kind of stage it was set during that particular time? Because IISc physics department has outstanding physicists who have looked at various aspects of condensed matter physics, and Professor Rai Chaudhary, and taking that lineage further, Arindam, now you have been actually looking at these problems in a systematic way. Could you please set a kind of a picture for us how it was working then?
I mean, at that time it was a GMR region, the giant magnetoresistance era, right? Early to mid 90s. And perovskites with the group of CNR Rao and Arups, and there are several other here. They were doing fantastic work on GMR. Now, one of the good things is that Arup wanted to measure noise in GMR as well, the perovskites as well.
Perovskites.
Yeah, perovskites as well. But his original, at that point of time, I was talking early to mid 90s, to STN and various other techniques. So he was trying to get different techniques coming together, including noise later. But I personally didn't do noise in perovskite independently. My junior did that after the noise measurement setup was ready. My connection to perovskite per se is limited because I find it's very complicated and complex for to make a very definitive conclusion using noise measurements, because noise can be impacted by very large amount of details. See.
You're right. Absolutely. So, which also means that the connection what you're making, because first of all, condensed matter systems, like so-called solid-state systems, what you're working on, you're also looking at from a many body viewpoint, and now associating some of the things which are coming out in terms of the noise, and looking at the statistical averages of currents and other properties. So it also means that you are now trying to bridge condensed matter physics with some statistical viewpoint, and this kind of amalgamation of two subfields of physics results in very interesting questions, right? Because this also can lead to some new viewpoints on how, for example, electron is transported within that particular environment and other things. So during that time, were you also simultaneously kind of looking at things from a fundamental theoretical viewpoint? Was there any kind of efforts towards that direction?
Yes, I mean, I would catch up on the comment you just made, Pawan, about the statistical viewpoint, how we look at a condensed matter system. What we did is we started measuring noise, and noise means that you will essentially look at a fluctuation beyond its mean, right?
Yes, you're absolutely right. Yeah.
While doing this, I realized that we have created a technology in IIC, and which can go well beyond that.
Mm-hmm.
So we
Mm-hmm.
started doing statistical analysis of higher order moments of a physical property, whether electrical resistance was easiest, and that's what we measured most of the time. And we
Nice.
realized that it's not just beyond the mean fluctuation that is of information, but
Mm-hmm.
it's the moment of those fluctuations that could be as informative as ever. And actually, it turned out that when you go to the fourth order moment, that is
Mm-hmm.
kurtosis, and that is the kurtosis. Skewness
Yes.
is third order moment.
Third order moment.
Kurtosis is fourth order moment, and you go on like that. Kurtosis seems to be more informative about structural transitions and long range order in a condensed matter system than the noise itself. Noise gives you a certain initial resistance. Normal mean measurement says nothing, but says very little. Noise gives you a little bit more information, but if you go to skewness and kurtosis kind of moments, it actually becomes really fantastic and far more direct approach to understand the physical properties
Physical
of
properties.
the systems. Yeah.
Oh, wonderful.
So, as far as the experiment theoretical part is concerned, I would say my work was more towards understanding from an experimental perspective how a physical system will evolve in its statistical properties in a higher order statistical moments.
Yeah.
And there were already theories that were being developed. So I didn't do them myself, but I used those theories for my experiments.
Wonderful, wonderful. So now you're armed with this intuition of knowing how systems work from a noise, a one by noise viewpoint, and with this intuition, you're now stepping out of India. So paint us the picture of your transition from India to UK, especially, and also maybe some things in between, which is happening at that particular cusp in terms of your physics interests and what kind of research you are now thinking about.
Yeah.
What is your thought process? Yeah.
So the thought process was very simple. And thought process was that I will not do the kind of physics that I was doing in India during my PhD.
Okay. Okay.
That was my first criterion in choosing my next step. This is something which I always tell students who are finishing PhD is, you see, postdoc time, if you choose to do postdoc, is the last opportunity you will get to learn something at somebody else's money. Because you are being paid to learn something, so you take the maximum leverage on that opportunity. So I wanted to do something different. I had multiple offers. One was to continue measuring noise.
Yeah.
So I did not want to take that, but I wanted to go to Cambridge because Cambridge gave me a certain degree of flexibility and freedom to do whatever I want. I mean, it's also, you see, all the time I always look for an option which gives me a maneuverability, a space to do things that I want to. And I went there and learned about semiconductor processing. And today I am reaping the benefit of putting two worlds together, my noise measurement background measuring electrical signals and my device background, which is why my group is quantum materials and devices group.
Devices.
When
Absolutely.
I came back to India, Pawan, I felt that that aspect of making devices for physics was absent.
Wonderful.
And
Wonderful.
that I learned in Cambridge. So that's the advantage of the transition period, that decision that I took, that I have to learn something which I didn't know during my PhD days.
Wonderful. So this is also an important point which we're going to elaborate a little bit more once we come to your own research, current research interests and other things. And the fact that you are now going from, let's say, this one by f noise viewpoint to slightly more device based physics approach, which is a very important viewpoint. For example, if you look at Federico Capasso tells doing physics by design, right? Because that is
Yes.
you really produce materials and also build things which is slightly more hierarchical and bring out new physics. And this approach is very effective. And as you mentioned, it also needs a little bit of training and infrastructure. So how was your training and kind of exposure to infrastructure at Cambridge? Of course, you were at Cavendish Laboratory, which is as
Right.
people should be knowing, is one of the greatest experimental physics facilities ever ever constructed
Yeah.
in
Absolutely.
any place. Yeah, yeah,
Yeah. So,
yeah.
Pawan, this is a fantastic question that you asked.
Mhm.
You are absolutely right. Going to Cavendish and understanding the infrastructure and utilizing the facilities, etc., was a great experience. It was a learning period for me, and also the training and getting exposed. But I have to say, the biggest advantage of going to Cavendish at that point of time of my career is to
Mhm.
learn how best minds work, how they
Wonderful.
imagine what, and the fact that they are not scared of imagining and then trying to execute them. That was my biggest gain, and that was what I when I returned to India, I got back with me, so that
Mhm.
you need to know that if there is an idea, that you have to execute it without feeling that okay, it will be constricted, what will be the outcome, etc. So that was the Cambridge culture that I always felt very strongly influenced by.
Wonderful.
In India,
Wonderful.
I came back at a time when this structural change was happening in the scientific ecosystem.
Yes. Yes.
Money was coming in. I When I came back to give my job talk at IIC,
Mhm.
um,
Mhm.
the reason I decided that this is the right place to come back was that's when electron beam lithography machine was first time being installed in IIC.
Installed.
It was
Absolutely.
one of it's the bloodline for my group. If I have to make devices to design physics, to emulate physical interactions, then you need the basic minimum. I always say that there are three facilities that you require. You
Mhm. Mhm.
need a high quality measurement facility. In India, high quality measurement facility was partially there by the time I left India as a PhD student.
Yes.
You
Yes.
need high quality device making facility, and you need high quality material growth facility.
Material growth.
these are the
Yes.
three these are the three pillars on which experimental physics needs to be built. When I was going off, experimental measurement facility was on the high. When I was
Mhm.
coming back after my postdoc and trying to find a job, I felt that India is ready to do the second one, that is high quality characterization and device making facilities. So unless you know
Wonderful.
what is material you have, there's no way you will do a good job. Right? So electron beam facility, the TEM facilities, etc., are
Mhm.
for the first time was being installed at a large scale at IIC, and that made my decision to come back easier. And
Easier.
as soon
Yeah.
as I came back, we got into the device making. Yeah,
Yeah. Yeah. So this is roughly around 2005 or something like that,
six,
right?
five, six.
That's
Yeah,
5, 5, 6. Wonderful.
yeah.
See, one of the things which is also kind of oblivious in all these things in your formative years is that you have already got exposure towards low dimensional systems. It actually became important as one actually emerged into 2000s, that nanotechnology got its kind of a prominence. But you can see that even before that became an important topic, you already are kind of working and playing around in that particular area. How was that time like? Because nano was a very important topic then, because there was also an
Yes,
equal participation from both chemistry viewpoint and physics
yes.
viewpoint, because materials meet at this particular junction very beautifully. And
We That's right.
how was your kind of thought process at that particular time from
Yeah,
this nano viewpoint? Yeah.
yeah. No, no, absolutely. You got it spot on, Pawan. See,
Mm.
the nano in India at that point of time was a top-down approach. What I mean by
Mm.
that is that we
Mm-hmm.
used to make nanoscale systems, but we used to measure them when it was in a macroscopic form,
Form.
right?
Yes.
Because
Yes.
because we had, I mean, at least through the 90s and very early 2000s, we were making systems, we were getting into nanoscale region. We know that this is how the nanoscale systems will look like, and we also knew that nanosystems will have new functionalities, new physics in there, but we didn't have the facility to go to the nanoscale system at individual level and look at the physics. When I
Physics.
came back and in 2000, mid 2000s, that's when things that possibility started becoming reality for India. So we were doing the bottom up.
Bottom up.
So what we wanted to do is that we go to the nanoscales and prepare them at the nanoscale. And graphene at that point of time was a perfect example that you thin it down to the single atomic level. And then you start making devices from there, allowed us to look at nanoscale systems in a new manner that was there other places in the world, but not in India at that level. So it opened up a whole new physics. It opened up a whole new area for us.
Wonderful, wonderful. It's also very interesting because you're now making a transition circa 2005, 2006, and graphene is just emerging around 2004. It's a very interesting time, right? Because
exactly
the buzz around graphene was unbelievable, right? Because
yes.
Maybe initially people probably were a bit hesitant, but later on, once they start that Klein tunneling paper in Nature Physics, that beautiful cover page of Gaim and Navaslo, that really changed the game. And you were actually in the thick of that kind of transition, because I think you were already kind of exposed to that, given the fact that the UK was already working on these problems, maybe in conferences and other times. Can you paint a picture of that time when you already are looking at this kind of emergence of 2D materials?
So it was interesting that you say, because I think the first talk by Kostya Novoselov on graphene outside Manchester was in Cavendish Laboratory when I was in the audience.
Wow.
This was after they have published the paper in Science in 2004 October, or around that late October. And 2005 January or late 2000 October, around that time, he gave a talk in Cavendish about graphene, the new material that they have created in the laboratory and tried to measured their electrical properties. Coming to the question, yes, of course, I knew about graphene, and there was no doubt about that in my mind, that the moment I start and get my opportunity to start my research group, I'm going to start looking at this material 2D, because I already was working in 2D materials and gallium arsenide, semiconductor, high mobility electron gases. And this was easy to make. And like many people of my generation at that time, this was essentially a scotch tape and having a student here.
Absolutely.
So I remember when Atin Pal, my first student, joined, we sat at 2:00 in the morning and trying to make graphene sheets on silicon oxide substrates. For a young assistant professor, this was an absolute stardust. Exactly. Because you can be productive, you can look at very interesting physics at very low cost.
Absolutely right.
Helps you in establishing yourself. But then, of course, it was certain that we end up from there. Then by 2012, 2009, actually, the graphene has expanded its family. Molybdenum disulfide came into play. 2009, right? It's,
2008-9 maybe.
2009-ish, I think. I have to check
you're right.
the exact time scale here. Andruskis from EPFL came up with the molybdenum disulfide. And the world has not been the same again. If you look at the scientific landscape, look at the number of people still working in this field, and it's going to industrial and particularly the TMDC semiconducting parts. We started that, and then 2012. I always say this. You see what we did the first time. So in 2004, Manchester came up with graphene. 2009, EPFL came up with molybdenum disulfide, and we were the first one to combine those two.
Very nice.
And
very nice.
We showed that not just you have fantastic properties of graphene, already people were understanding. You have fantastic properties of molybdenum disulfide, people are understanding the light emitting properties, the electronic properties. We showed for the first time that by putting them together, you get emergent properties. You have properties that were not available in these two. So that's how the 2D has grown in my group, and it continues to grow towards technology side.
Wonderful, wonderful. Uh, Before we also come to some of the very important work which emerged out of your group, one of the things, if you also observe in Arindam's work, is that this aspects of 2D electron systems have already been worked on, especially in your Cambridge times. I think you also did a lot of interesting measurements. Do you want to tell what kind of measurements they were, and what kind of problems you are looking at, and before we jump into your research as an independent researcher? Yeah.
Sure. So in
Mm,
Cambridge, I was looking for strong Coulomb interaction effects in 2D, particularly
mm,
mesoscopic 2D. That is where the size is in the order of a few micrometers, and the size of the sample is similar to the length scale of electron dephasing
mhm,
length scales.
mm,
My goal was primarily to see if you go to very strongly correlated systems like at low density electron gases, whether
mhm,
the system becomes magnetic, whether the
magnetic.
spontaneous spin polarizations arise, or whether there are Wigner crystals of electron crystallization or any other new phases. See, I'm talking about a region or a time where the metal-insulator transition in 2D was a very big topic.
Very big thing.
Was,
Yes. Yeah.
right?
Mod
There used to
mod
be,
translate. Uh,
yeah, more transitions, and whether the question was whether you can have a metal-insulator transition in 2D at all.
mhm, mhm.
And there
Wonderful.
were huge amount of controversies going on. My work in Cambridge was in the backdrop of those debate,
Those debate.
and we were looking at possible phases in 2D when you make the electron-electron interaction very, very strong.
Wonderful, wonderful. So now we're going to slowly make a transition to your work. Among them, of course, you also got started with the two-dimensional materials, and also to certain extent, you're also looking at some nanowire systems, which is also very interesting system because it's quasi one-dimensional, so to speak. So the
Right.
behavior of electron sometimes might be very different from a conventional two-dimensional system. So how did you get interested in this quasi one-dimensional nanowire systems, and what was the
Right.
motivation?
Noise. So I have an
Noise.
idea
Mm.
here, noise.
Mm-hmm. Mm-hmm.
Because what I felt is that, okay, people have been looking at these one-dimensional magnetic systems for racetrack memory and various other
Mm.
applications,
Yes.
which
Yes.
I understood that is a very important technological direction. But
Mm-hmm.
understanding the movement of these domain walls
Mm-hmm.
in
Mm-hmm.
one-dimensional magnetic systems were usually done by using either imaging of Moog type or doing electrical properties like resistivity measurements and so on.
Wonderful.
So we
Wonderful.
realized that the noise could be a fantastic way of looking at the movements of domain walls in the system. And at that point of time, I was also looking for new systems to try out noise, and this one was
Wonderful.
graphene was the other, of course.
Yeah. Yeah. Wonderful. See, one of the important, kind of benchmarks which emerged out of the work, mainly based out of India, was your paper on a hybrid of graphene and MOS2, where you started now looking at not only in terms of condensed matter system, but a possible memory device, especially which is responsive to light. There is a very fantastic paper. I would of course link it in the show notes, where Arindam and co-workers looked at photo responsive memory devices, and that really, it was one of the very, very fascinating works to come out of India. And I should mention, across the world, it actually played probably a very critical role in looking at making photo responsive devices using 2D materials, especially in hybrid architectures, given that graphene was not generally a kind of a candidate for a photoresponsive material. Uh, how did that idea come about? Can you please tell a little bit about that work, Ridhu?
Sure. I mean, first of all, I have to say that that was my first work in optics ever.
Wonderful, wonderful,
Okay,
wonderful.
I have been an electronic person, and
Yes, yes.
we can measure electronic properties in materials for many years, but I never did any work on optics or looking at how light get converted to electricity.
Let's.
Never,
Okay.
ever. So
Okay.
it's all again a very happy coincidence with
And
having fantastic students. I was
yes.
already 4 years old here, 5 years old in ISC,
Mm-hmm.
and we were discussing over a cup of tea that okay, we have this beautiful heterostructure. We 2012 when we submitted the paper. Earlier that year, there was the first paper on these heterostructures of graphene on boron nitride, where it
Yes. Yes.
showed that it increases the electrical mobility of the system. I had
Yes.
2 or 3 absolutely fantastic students, and they are
Mm-hmm.
they're all professors now in different parts of the world.
Wonderful.
And we were discussing over, and they said, okay, what about, we know how to make molybdenum disulfide field effect transistors. We just published that a year earlier.
Mm-hmm.
And we know we have been working on graphene for a while. What happens if we put them together? Pure and simple scientific fun. There was no suggestion that we will be able to do anything. It will go anywhere with that. So then we went to the lab, and the students, they put them together and put contacts on graphene, and then realized that hey, when it is in the daytime, when it's outside, its current is very different from when it's dark and inside a vacuum chamber.
Wonderful.
So
Wonderful.
we realized that something else is happening.
Mm-hmm.
And then we started doing this experiment. And initially, the experiment was actually as a memory bank. And when we wanted to publish this paper, we sent it to Nature Nano, and then we probed it. Okay, look, you shine light, and the current changes, but it doesn't go away when you turn the light off.
Yes.
And we understood that why, but we did not try to portray it as a photo detector. That's only when we started calculating the power of light that we actually, the interesting part was the paper rejected, Nature Nano rejected the paper.
Oh,
and said that okay, this doesn't seem to be particularly interesting to us.
I should pause here, and I should mention that as of today, which is 3rd of September, this paper has been cited more than 1,400 times. Okay, so probably even more than that. At least the stuff. So you can just imagine that things which get rejected actually have sometimes deep impact. However, please continue.
Yeah.
Maybe the story
No,
would be.
you're absolutely right. So they rejected the paper and said that it's not particularly interesting to us.
Okay.
And then we went back and we found that we redid the calculation, redid the analysis, and realized that the power that we are shining on this hybrid was very, very small, and the resulting current was unusually large. So then we calculated and we realized that the number of power divided by the current, or the current divided by the power, is 10 orders of magnitude more than any optoelectronic element that you see in our cameras, etc. 10 billion times. It's a very large number. So that's when we realized that there's a paradigm shift in many ways in material design. So then we wrote back the letter saying that, look, you rejected the paper, and look, this is something. And then they were very supportive. They immediately took the paper, sent it off to review. It took us 1 year to get the paper published. You can see that it's exactly 1 year.
Yes.
But it is still the first graphene hybrid optoelectronic paper in the world. Yeah.
Absolutely. So you can also see that the kind of intuition which is developed in that particular paper is also going towards the so-called van der Waal heterostructure kind of an architecture, because this is kind of a preamble. Maybe during that time, that van der Waal heterostructure still was not in the limelight. Only when Guy wrote that Nature kind of review article where he gives the all the stacking probabilities and other things.
Right.
But this was already seeing the problem from that viewpoint. So these van der Waal heterostructures also have turned out to be important optical materials, and this is kind of a preamble to all those kind of problems. In terms of the work, what already has been done, especially from your own laboratory, and also many other groups have taken it in new directions. Is there anything very specific which you want to comment on? How this work actually influenced some other work and other things?
Of course. See, van der Waals interaction heterostructures is a fantastic platform of, as I said, synthesizing interactions in nature. at
Absolutely.
the from its building block.
Mm.
Essentially, suppose you take a solid and you start slicing it up, and
Mm.
you ask the question, okay, eventually how the two successive layers of atoms interact.
Mm-hmm.
You can
Mm-hmm.
emulate that, engineer that, modify that in a van der Waals heterostructure.
Wonderful.
So I,
Wonderful.
after 2011, when or 12, after the whole van der Waals heterostructure came, and we
Mm-hmm.
started making in the laboratory, it sort of became the chief graphene extension worldwide,
Mm. Yes. Yes.
and to decide new functionality and new physics. 2018, superconductivity came, is also a van der Waals heterostructure where you are modifying the band structure, modifying the electronic energy spectrum using van der Waals heterostructure. So, and it's growing even today, looking at functional aspects. For example, we ourselves have made
Mm.
memories for neuromorphic computing. We made
Mm. Mm.
thermoelectric devices. There are other people, optoelectronics, of course, has been going on for a while. Okay, superconductivity,
Mm-hmm.
new kind of optical states in semiconducting van der Waals heterostructures, quantum single photon emitters, single photon detectors. Look at the breadth of
Correct.
technologies that this van der Waals heterostructuring concept has led to.
Absolutely. Absolutely.
It
Absolutely.
has taken the 2D material field in a very different platform, to different plane of it.
Absolutely. Absolutely. That library, what it has generated
Exactly.
is
It got infinitely expanded, not just by the different chemical genre of materials, but
mm,
after that, since 2018, every angle. So really, the library has become infinite.
infinite. Absolutely. So before I make a transition to your current work and also some of the things what has been developed in terms of quantum technology and other things, I would also want to make some kind of observations on your work on phase transitions before the transitions, the actual phase transitions, because that is also something which your group worked roughly around that particular time, 2010s to 2013, 14, and other things.
Right.
Uh, Phase transitions are at the heart of condensed matter physics because
Right.
they are probably one of the most important fundamental kind of criteria on which materials actually are looked up.
Yeah.
Uh, what kind of work came out of your lab? Could you please tell us a little bit about that?
Sure. So there are
Mm,
two types of phase
mm,
transitions that we look for. First is electronic phase transitions,
mm, mm.
metal-insulator transition, magnetic transitions, charge ordering transitions. These
Yeah.
are electronic transitions that we look for. And the reasons we could make such experiments and have uh, a new perspective to add is because of our ability to do noise measurements.
Mhm,
We
mhm.
looked at we could make the noise measurements and electrical measurements simultaneously. We showed that when an electron moves from metallic state to a kind of insulating state through the metal insulator transition point, the Mott transition or Anderson transition, there is a regime of glass formation. Electrons become very slow, for example,
Nice,
and the
nice.
noise goes up massively. So this is
That's
electron glass, something a new phase that has come up at the intermediate phases. But then we also showed that the noise can be equally interesting tool to look at structural phase transitions,
phase transitions.
even if
Wonderful.
it is a tiny amount of atoms which are restructuring themselves in a new structural phase. And this is why our ability to measure moments of fluctuations became such an important
Important part.
tool to look at those. And we have realized that what are the fundamental aspects of such structural phase transitions. The
Mhm.
equilibrium, are they with a thermal equilibrium phase transitions, or whether these transitions happen athermally, away from
Mhm.
thermal equilibrium.
Tamil.
All these questions become available, and we could make certain aspects, certain comments on that. And I think those are very interesting pieces of work, which will always be very close to me. Actually,
Wonderful. Yeah, yeah. Also, I should mention that all these things are done uh, not as a kind of a black box measurement. I also saw that you people actually had to develop various different experimental methods, and including tunneling microscopy techniques and electron
that's correct.
microscopy methods.
Yes,
These are important peripheral methods. In fact, in
right.
many times these become central to the experiments what we do.
Oh,
So
yes, absolutely.
so, uh, so it means also that there is a lot of emphasis given on the instrumentation part of it,
Yeah,
which is
yeah.
very important. Would you want to quickly comment on that, and then we'll move to the
Absolutely, very quickly. Actually, I'll give you an example. So there was this paper that we wrote 2017
Mhm.
on looking at graphene exfoliation and how to monitor the electrical resistance of the graphene which is getting exfoliated while getting exfoliated. So
Wow.
what we did is that we had a scanning electron microscope in my group. I bore a
Mhm.
hole through it and
Mhm.
put
Mhm.
in electrical contacts in that and made a tip come to the graphene under an electron beam and image the exfoliation process while measuring the electrical conductance through the exfoliate at the same time at the junction. And we realized that when you exfoliate materials, they don't exfoliate randomly.
Mhm.
Nature
Mhm.
has certain preference
Preference.
in creating structures. We found that the exfoliates happen in 30 degrees or 60 degrees specific angles, and we could go down to measuring electrical properties when there are just two hexagons are connecting the bulk graphite and the graphene exfoliation. All these require instrumentation.
Wonderful. Wonderful.
Instrumentation is the key, and we need to continue with this culture. This is something which I
Absolutely.
always emphasize in my group.
Absolutely. Wonderful. Wonderful. So now we're going to make this transition into your current research, what your lab is actually also looking into. One of the aspects which has emerged in recent times is this important mission of quantum technologies, and you are spearheading some of the efforts which are going on in India. Uh, Not only in terms of the work which has to come in future, but your lab has already done quite a lot of work in this particular area. Could you set us a kind of picture of what are your current research interests? What has been your motivation to look at these problems? Where is the fundamental physics going towards? And also, I'm very sure a lot of technologies which are emerging out of it. Give us a picture of this particular
Yeah,
aspect.
I mean, so my lab right now is in a position to look at both technology as well as fundamental aspects of quantum state manipulation, understanding um, new platforms for quantum, all quantum verticals, quantum
Mhm.
computation, communication, and sensing. So, for example, the way my research group is divided is that because of our um, expertise and the track record in 2D, we feel that
Mhm.
2D is a
Yes.
very strong candidate in certain areas. For example, in photon detection, quantum
Yes.
single
Yes.
photon detection is one of the most important aspects. So we would like to take that to a more technological level because we believe that there is a scope of new technologies for 2D for single photon detection because we would like to have high efficiency, high temperature operation, broad spectral range. You know it better than anybody else in this area of optics and
Mhm.
quantum optics. So we are trying to take our fundamental work that we have done over the last nearly a decade to quantum technology. So that has matured enough to take
Fantastic.
an impact detection or sensing technology for quantum applications. In addition to that, I'm also trying to get into state manipulation, cavity mode coupling, etc.,
Coupling. Okay.
in which I would like to use our understanding of quantum states, optical states in 2D, for example, in molybdenum disulfide or TMDCs, whether we can cavity couple it and
Mhm.
using our ability to make van der Waals heterostructures, whether we can create new readouts of quantum states
States. Yes.
rather than see most of the optical manipulations are done and it's usually read through optical means like
Mhm.
photoluminescence, like
Yes.
things,
Yes. Yes.
techniques of that sort. But with our ideas of van der Waals heterostructures, we believe that we can make an impact in these areas of readouts in quantum processes, quantum states. So we are working in that direction. We are now working towards making uh, quantum devices of 2D devices with cavity coupled in various Bragg reflectors, etc. So this is my 2D in areas of quantum. But in addition to that, I must emphasize that we have been continuously expanding or pushing the limit of the quality. of
Mm-hmm.
materials
Mm-hmm.
in 2D,
Materials. Absolutely. Yeah.
because one of the key problems in both India abroad as well, but India in particular, is to create metrology quality material.
Mm-hmm. Yes.
And
Yes.
for example, if you want to make a resistance standard using quantum Hall, you need high quality material, high
Mm-hmm.
mobility electron gases. And we in India need to put in a lot of effort in that and need to build infrastructure. My group is looking at extremely high mobility graphene devices. We have made now one of the best, highest mobility graphene devices ever created. And we would like to take this work towards metrology standards. So that also comes under the quantum mission and mandates of quantum activities.
Quantum activity.
Of various
Yeah.
types.
And it probably also kind of resonates very well with the semiconductor technology is also
Yes,
an important
exactly.
aspect. And
Yeah.
I know that you also are taking initiatives and also interfacing with the government on some of the initiatives in terms of formulation and other things. uh, See, these aspects of condensed matter systems, either from semiconductor viewpoint, insulator viewpoint, or magnetic material viewpoint, and things like that. This kind of so-called verticals have become extremely critical in terms of broadening the technological, base of the
Landscape.
of
Yes.
landscape and other things. Do you think there is also enough effort going on in the country? What is the general viewpoint? What you have in terms of the research which is going on across India, especially, and of course the global emergence has already been there. There's a lot of interesting work which is recently kind of emerging out of this, especially in moire kind of materials and other kind of things. Would you want to elaborate a little bit about this?
Yes, Pawan, the problem in India is the number of people. I
Mm,
think
mm,
I think India has, at least in certain selected places, India has the infrastructure,
mm, mm,
but it's far too few and far too few users,
mm,
and it's
mm.
extremely top down.
Yeah, yeah.
As a result, if you look at the ideas and look up some of the work that is coming out, yours included, they are
Mm,
fantastic pieces of work, but they're so few in number because at the end of the day, certain faculty members will do a certain amount of time because there is a limitation of 24 hours in a day. So while many of these existing technological directions in using 2D and beyond, I work beyond 2D as well. Um, uh, they are the top-notch work. We
mm,
have in certain places coming out the best quality moire infrastructure,
mm, mm,
moire making facilities. Right?
mhm,
We
mhm.
have fantastic control. There are
Yes,
students and faculty members who are continuously working and churning out highest quality work in this direction.
true,
There are
true.
people who are taking this into technology as well, but the
Mm,
effort volume is extremely low. And this
mm,
is a problem that when you talked about me getting into certain policies and
mm,
understanding how the government is thinking, I whenever I get time and opportunity, I tell how to enhance our
mm.
critical volume of people working in any science and technology directions.
Absolutely, this aspect of critical mass, so to speak,
Yeah,
is
yeah.
so important. So now converging towards science plus society
Yeah.
of your work, and I should also mention that people who have heard Arindam speaking, he's one of the outstanding seminar kind of orator in terms of science, and also slightly more on a broader context. He has had also a wonderful exposition in terms of the way science has to be done in from an experimental viewpoint. And this has also resulted in you, as I mentioned, interfacing with the policy forums and other places. So one of the pressing points, as you already mentioned, is the emphasis which we need to give to broaden the base, and 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 that particular foundation is laid by graduate students, PhD students. One of the pressing problems which we find, especially in terms of the support which we can give to our PhD students, has been a very crucial element, and which has to
Exactly.
be given emphasis about. Would you want to give us a little bit of a broader kind of a viewpoint from your side, how we should be able to take the problem further and solve this especially in encouraging young researchers?
Yes. So we have made several recommendations in various forums, including the upcoming policy, new education policies, as well as
Mm.
the the NRF, National Research
NRF.
Foundation,
Yeah.
various types of forum. I think there's a sensitivity from the government also, but
Yes.
everything takes time because there are a lot of other bureaucratic bottlenecks that things have to go through. In India, if you ask me, the problems are twofold. One
Mhm.
is the disconnect between universities and research institutions.
Mm.
As a
Mm.
result, we lose out a very large number of students who would otherwise take up challenging PhDs or higher education in general.
Absolutely.
So this is something which is a crucial problem that needs to be sorted straight away.
Mm. Mm.
If you want to increase the number of people, to broaden the
Mm.
base, that's what you say. The second thing is that how we can create a better and more versatile training mechanism within the existing structure.
Mhm.
One of
Mhm.
the problems is the postdoctoral structure
Absolutely.
and the
Absolutely.
technical research slab that nearly is missing in India. You see, today ISRO is doing a fantastic job because it has
Mm.
got a large number of people who have taken doing science and technology as a career option for a longer term. In the academic sector, on the other hand, you see that the people who are there are either the PIs, who have got
Mhm.
5 students or whatever number of students, or the research students. Of course, you need to create a research studentship as a lucrative career option, but that becomes a lucrative career option not just by paying more money, which is essential, of course, but also giving them the impression of the next step. What will be the job prospects of
Job
them? If
prospects.
every student sees that the job prospect is becoming a professor somewhere, it is not a viable career option.
Absolutely. Absolutely.
You need to create an infrastructure where the student can see that after doing a PhD, I can go to industry, I can be a long time career in science. So a slab of that sort must be created, which will help not just enhancing the quality of the science, but also the quantity of the science.
Quantity of this. Absolutely.
So
In
the
fact,
ability to create, sorry, just last point.
yeah,
A
please.
PI can guide realistically about 5 students. If you create an option of having scientific slab, technical slab in between PI and the students, a same person can guide 10 students, 15 students, 20 students. Your
Fan-
efficiency goes up dramatically.
Absolutely. This is a very important point. In fact, I would also refer to one of the opinion pieces you wrote recently in Indian Express, which actually was very illuminating, where you do mention about skilled workforce and what actually can be the prospect if you have that kind of large skilled force. The other aspect is also the culture of experimentation. That is something which we kind of touched upon in slightly more indirect way, but this ability to look at things from an observation viewpoint and connecting it to abstract pictures and abstract questions is something which is very critical, and it is something which should also be inculcated within our education system, and a culture of building instruments skill based approach also is very vital. So what are your thoughts on that particular aspect? Would you want to just elaborate a little bit?
You see, this is something which is an absolute essential because we are now getting into technology mode, right?
Absolutely. Absolutely.
And if you want to go into technology mode, you have to demonstrate that you have the ability to do instrumentation. Today, whether it's Mars rover or whether it's Chandrayaan 3 or a quantum computer, it all boils down to how you make an instrument, go to the lab and go to the workshop and make a cavity with a superconducting aluminium to make a qubit, right? So instrumentation is an absolute key, and we must have workshop courses and exposure of students to workshops and experimental techniques at a very early stage of their,
Yeah. Yeah.
of their studentship in the undergraduate level in particular. So
Absolutely.
this
Absolutely.
is, it pains me that many of the laboratories in across the country are actually taking away the experimental course from the curriculum.
Yes.
It's
Yes.
the hierarchy of highest order. if you don't train people how to do instrumentation, how will you have technology in the country? Everybody will end up becoming software person, which
Software,
is
exactly, exactly.
not a healthy trend at all.
Absolutely. It also emphasizes the point that whatever is generally called as engineering need not be restricted only to software engineering. Because, for example,
Yes,
electrical, electronic, mechanical, civil, these are all
right.
so important because as an experimental physics person, you always have to interface with these domains of engineering too. And somehow, if a larger emphasis is given to that aspect too, it's
Particularly, Pawan, if I can add, I mean,
yes,
today
yeah,
there's so
yeah.
many government initiatives called Make in India,
Mm, mm.
Atmanirbhar India, etc., Startup India.
Yeah,
There are
yeah,
series of new, that's because there's a clear gap in
absolutely,
manufacturing. Why there's a
absolutely.
clear gap in manufacturing? Because we don't have people who take instrumentation. Manufacturing is instrumentation at the end of the day, whether it's a high
Absolutely.
end industrial scale or at a small biological pharmaceutical scale, right? So it
Absolutely
is
right. Absolutely.
instrumentation that we need to be exposed, we need to be open, and we need to be fearless
Mm,
in getting
mm.
into instrumentation and building something from scratch.
Scratch. Absolutely. Absolutely. That's a very crucial aspect to build something which is such a slightly larger base and also look at the viewpoint. Do you also think there is some room for us to improve on the general facilities which are provided for let's say colleges and universities at state level? Of course, NRF probably will
Yes,
change that particular viewpoint.
absolutely. And I will echo some of the things that I said in the case of NRF as well, and some whenever the opportunity came.
Hmm.
There are two ways in which universities and colleges need to be included. First, of course, building a basic minimum infrastructure
Mm, mm,
where the students can have at least a look and and association with cutting edge instruments and equipments of what people use in research. Number one.
absolutely.
But
Absolutely.
number two is very crucial. And number two is that we need to have colleges and universities to be associated with people who can write proposals,
Hmm.
research
Hmm.
proposals.
Absolutely.
What we find I'm on several committees of the ST and looking at various project proposals, etc. And I find what the biggest problem is that the universities and colleges often are are left behind when it comes to writing proposals on cutting edge problems,
Mm, mm.
and
You're right.
we require a serious mentorship. This
Mm,
is a human infrastructure that I'm talking about. It's
absolutely.
not
Absolutely.
equipments. We need active participation of tier one institutions. We need to use superannuated faculty members. We need people who have got fantastic track record to engage actively with multiple colleges and universities to tell them how they should propose cutting edge
Hmm.
science rather than doing incremental research. This is probably going to be a game changing thing for Indian science if we
Hmm.
can enforce such culture and in engaging colleges and universities.
Wonderful. Wonderful. See, one of the elements, if you take a slightly more meta viewpoint, Arindam, I am very sure easily you could have settled in the West because the both in terms of the talent, drive, and everything you had. What motivated you to come back?
Okay, so
Uh,
99.9% people, it's actually a certain level of connection to
mm,
motherland. I mean, if you see many people come back here because
yeah,
of that,
yeah.
I will be honest and I'll say that was 50%.
Mm,
Other
mm,
50% was I actually took a strategic decision to come back to India because I felt I will have better visibility,
mm,
professional
mm.
visibility from India
Yes,
than
yes.
settling abroad, not because anything else, but because I felt that the India was coming up as a country mid 2000s in
Hmm.
terms of its
Hmm.
research infrastructure. And if you are in a good institution, you will have opportunities and if you will have access to facilities which will probably be better than most places in the world. So it was not just pure connection to the motherland, which of course was there. Like many of you came back because you had that connection. But it also purely strategic and professional decision to come back. And I think that professional decision to come back is becoming more and more as we progress in our infrastructure. I think it's on the rise.
Yeah. Well, it's a very good thing to know, because this aspect of strategy is very critical, because a lot of people, especially at the cusp of their postdoctoral research and looking for positions, and there are many nowadays, given that there are also emergence of new IITs and other opportunities. And this is a point which many of them would be really pondering over and trying to make a decision.
I think people should take a longer term viewpoint and say that it's not about ease of lifestyle is something you have to be. Family is a very important aspect, but if I take purely professional viewpoint, I don't think India is a bad destination at all.
Absolutely. That's heartening to know from a person who actually has really made his career here. That's an important point.
I'm a test case. You are a test case too.
Yes. Yeah. I should mention that. So what is very, very interesting, before we also move to something a little bit more fun, where we're going to actually ask you to speak in your mother tongue. One of the aspects I would also want to touch upon a little bit of the thing is the Indian academia providing enough opportunities to be sensitive to diversity in terms of, let's say, gender, in terms of any kind of representation? As person who is not only a researcher deeply involved in your work, but also as a person who also has some kind of say sometimes in some forums where you can express your opinion. What is your notion, Arindam? Is India doing okay in terms of that? Is there room for improvement in terms of representation and things like that?
I would say, Pavan, that India is becoming more sensitive.
Absolutely. Yeah.
Rather than jumping and saying that India is doing more, because there is always scope of improvement. There's always scope of being there are two types of diversity I would like to emphasize on here. One is gender diversity. There is no doubt about the fact that we have to take serious action to to have better gender diversity in our professional sector, academic sector, and not just that, and beyond that as well. Most of the social sectors.
Absolutely.
I have to say that in most of the committees that I go to, conferences that I attend, in choosing the invited speakers, etc., the organizing committee, we are trying to make as much as possible, because there is a sense of need to diversify, gender diversity.
Absolutely.
There is, I'm sure it's going to happen, but it's a slow process, and things are improving for sure. But there's always scope of more improvement. The second thing which India is doing very little, I would say, is ethnic diversity.
Very good.
And
excellent.
I think as a country, we must look at diversifying our workforce in terms of ethnic diversity as well. It's only in top tier institutions that you see diversity from different parts of the country.
Absolutely.
And even worse, diversity from all over the world. Today, I know there is a question of looking at rankings of universities from the diversity, from global participation, etc. You don't have to go to ranking and improving ranking for this requirement, but I believe having ethnic diversity is essential to broaden your thinking processes.
Absolutely.
Cultural processes. For example, I'll give you a small example. When I had the students, postdocs who came from abroad, they were quite taken aback by the level of safety, the consciousness of safety that we followed in our lab before they came. That's because we got used to a certain type of work culture, And that didn't occur to us that the certain practices we had in the lab are not safe enough in the longer term. When the
Absolutely.
people come from other cultures, when people come from other background, they bring with them certain sensitization, or that's both cultural, professional, and professional.
Absolutely.
The background, their thought processes enrich us. So we became very sensitive, and we started practicing those safety cultures, etc. So this is what I meant when I say that we need ethnic diversity in Indian system, even though we have fantastic workforce, fantastic talent that we can choose from within the country. We
Absolutely.
must diversify ourselves ethnically.
Absolutely right.
We must make
Absolutely.
people from abroad come together and work with us, and
Absolutely.
enrich them and us simultaneously. So these are the two diversities that I am very strongly vocal about in whenever opportunity.
Yeah. Yeah. I've also seen that some of your group members also are from different parts of the world, not only just India.
At least they
At least
were, and yeah,
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 they
yes,
probably you had visitors and
you're
other
right,
people also
exactly,
coming in,
yeah,
which actually also is a very important part of it. Yeah.
exactly.
So now we're going to just change the gear a little bit, okay? Where I generally ask the guests on the podcast to talk something a little bit about their own motivations and interests in their mother tongue. And I know you have been away from Bengal for a very long time, but it would be nice to actually get to hear from you in your mother tongue, because I, what has happened is in the recent episodes, a lot of students from various different parts of India who listen to their guests in the mother tongue really get impressed upon the fact that you can also have somebody who is not only a scientist who only thinks in specific way, but also has
Sure,
other elements to it. So I request
sure.
you to just talk a little bit about your your
Okay, my
motivations.
mother tongue is not same as yours, Pavan. So I don't know what I would say, but but I'm going to uh, I'm going to say, because I had an occasion of interacting with Bengali newspapers. You know,
Nice, nice.
so they actually asked me to write something in Bengali, which I
Oh,
found very difficult to do, but
difficult.
because there is challenges in words.
Absolutely,
But I will
absolutely.
say a few sentences on বাংলায় কথা বলাটা খুব ইম্পর্টেন্ট, এবং বাংলায় সায়েন্স বোঝা বা বিজ্ঞান বোঝাটাও খুব প্রয়োজনীয়। কিন্তু আমাদের মাথায় রাখতে হবে যে আহ, বাংলায় শিখে এবং বাংলায় বুঝেও আমরা কিভাবে সেটাকে ডিফারেন্ট ল্যাঙ্গুয়েজে বিভিন্ন ভাষায় আমাদের এক্সপ্রেস করতে পারি, আমাদের কথা, আমাদের মাথা, আমাদের আমরা কি ভাবছি সেটা আমাদের বলতে বলার জন্য আমাদের সমস্ত ল্যাঙ্গুয়েজ, অন্তত ইংরেজি এবং হিন্দি, বা ইংরেজি ইন পার্টিকুলার, তার সম্বন্ধে আমাদের আইডিয়া থাকতে হবে যে কিভাবে আমাদের, না হলে যেটা হয় সেটা হচ্ছে আমরা যে কতটা বুঝেছি, আমাদের মধ্যে যে নতুন আইডিয়াস গুলো, যেটা আমরা একটা নতুন জিনিস ভাবার চেষ্টা করেছি, সেটা অন্যরা বুঝতে পারবে না। সেই জন্য আমাদের আমাদের ট্রেনিং, আমাদের শিক্ষা বাংলা, এটা খুব ইম্পর্টেন্ট এবং ইকুয়ালি প্রয়োজনীয় যে আমাদের অন্য ভাষার সঙ্গে কিভাবে আমরা নিজেদের এক্সপ্রেস করব সেটাও জানা।
Wow.
Pavan, I don't know how much did you understand. I just said that learning in Bengali is very important, but expressing ourselves in other languages is equally important, because at the end of the day, we have to be globally competitive.
Absolutely right. Absolutely right. In fact, this also reinforces the point of the diversification, because
Diversification.
diversity, it's also an internal diversification, right? A person who
Yes.
actually is studying something, and it's an important point what you really emphasize. In fact, what happens is generally students who do learn things in their mother tongue, uh, in India especially, have had some difficulty to make a transition,
Yes.
because there are not good
Communication.
communication tools and other things are not available. And
Correct.
hopefully the online capabilities of translation tools, etc., might actually come handy at some point of time.
Exactly.
Hopefully, yeah. Great. So now we are almost kind of converging towards the conclusion, so to speak. So I'm going to throw up few aspects which I would request you to kind of give your opinion on, especially in slightly more lighter way in terms of your
Sure.
influences. Because as I told at the beginning of the podcast, that a scientist is not a one-dimensional person, so to speak.
True.
There are multiple dimensions to the personality, and you already emphasized the importance of sports. Is
Yes.
there anything else you do, Arindam, to kind of relax, to kind of chill out a little bit?
Gym.
Gym.
Sports and gym are yeah, I go to gym very often, and I keep I make students go to gym, and so I have managed to tell them that, look, forget about sports. I mean, many of them are in active sports, but I go to gym. I go to gym. I need to go to gym for about 3 or 4 days in a week at least.
Wonderful.
So that's one of the aspects that I have to say I do. I love looking at Big Bang Theory and Two and a Half Men. Those are my favorite sitcoms. It is I never. I mean, now they're over, but I keep on rewinding and looking at them. So those are my relaxation processes when I'm sitting at home. I have to say, uh,
Wonderful.
it's yeah. I mean, and I have a culture in the group of going out for dinner.
Yes.
I
Yes.
We take any opportunity to go out for dinner. I mean, at least before COVID, it was far more rampant than now, but I think we're slowly building up.
Nice.
So whether it is a new paper, or whether it's somebody's birthday, or whether it's somebody has just joined,
Mm-hmm.
um, and we have I mean, I also have a culture with my family. So we all the members of the family sits down on one of the evening on Saturday, and we all watch movie together. We call it movie night.
Wonderful. Wonderful.
And those are things which keep me going. Actually, it's quite fun.
Wonderful. Wonderful. That's fantastic to know. So, yeah, is there any free time you do get at all, other than the
I
work?
mean, there is nothing called free time. Pawan,
Yeah.
you
Yeah.
you know it. We are academics. One of the things that we do 24 hours back, but there is something happening in the back.
Absolutely.
Right?
Absolutely right.
There's nothing
Absolutely.
called there is nothing called free time. But yes, I try to stop that by going
Mm.
to the gym or by going to Starbucks for a coffee and things like that. There's
Wonderful.
no other free
Wonderful.
time. Sorry, no.
Absolutely. Absolutely. Yeah. There was a very famous book written on Newton, and the title of the book was "Never at Rest."
Yeah,
you
that's
know.
right. I totally agree. I mean, I'm sure you agree too. So.
Yeah, true, true. Absolutely right. Absolutely right. So finally, I would request you to tell a little bit more about your future kind of directions in which your work is going to lead both you and your laboratory into. What kind of interests and what kind of things you would want to do, and please tell us a little bit about that.
Right. So, Pawan, as I get older and I get more into more policy making responsibilities and make have say at a broader forum than just my laboratory, I think the time is going to get divided. There is no doubt
Yeah.
about that. I have the structure going on in my lab already, which I have created over the last 15 years, in which there would be certain focused directions of my research, which will see, there was a time when I was doing anything that I felt interested by. So whether it's magnetic nanowire, superconducting systems, ultra thin films, then 2D materials, everything that I felt, oh, okay, this is fantastic, very interesting, I used to jump to. Now that focus, that needs to be focused. So I'm
Yes.
now moving towards more technology oriented, making real impact with all the fundamental understandings and technologies that we develop in the lab. I would like to make an impact in, say, quantum technology is one of the directions that I feel very strongly about. So in addition to that, I'm now involved in some of the national level activities, both in
Yeah.
quantum and in education. So I think with time, these are the two areas that I'm going to divide my time to
Nice.
see how things develop. But I think you cannot take science out of a scientist. So
Absolutely. Absolutely.
I think no matter what kind of other work I'll do, there will be a certain part of the day where I will sit and read papers and try to get new ideas. I'm sure you can relate to that.
Yes, absolutely,
So that's how
absolutely.
I'm going to go.
Wonderful, wonderful. I wish you all the best for the ventures what you want to take up, and also keep motivating, keep inspiring all of us with not only doing good work but also being a very good person. That's something which need not be compatible in many people, but I feel that that is one of the hallmarks of Arindam. Whenever you speak, even when I was moving and trying to build my own group about a decade or more, Arindam was one of the guiding lights for a lot of people like us. So thank you, Arindam. Thank you very much
Keep
for
on.
the time you spent on Pratidwani, where we try to humanize science. And
It's a
I'm
pleasure.
hope.
It's a pleasure.
Thank you very much. Thanks a lot.
Thank you. Bye.